Welcome to the Future Lab, everyone. I'm your host, Matthew, and today we're diving into a truly groundbreaking research paper that's revolutionizing materials experimentation. This paper details Archerfish, a system that uses 3D printing and some seriously clever engineering to dramatically speed up the process of discovering and testing new materials. Now, the search for new materials is the lifeblood of innovation across so many industries, from energy and electronics to medicine and manufacturing. But traditional methods? Let's just say they're slow, painstaking, and incredibly expensive. Imagine a world where we could synthesize hundreds of unique material compositions in a single minute. Sounds like science fiction, right? Well, this research paper brings that vision closer to reality with a surprisingly low-cost solution. Before we get into the nitty-gritty, I should mention that this episode's script was AI-assisted. It's a testament to how AI is transforming not just scientific research, but also podcast production itself. So, what's our roadmap for today's exploration of Archerfish? First, we'll explore the research goals. Then we'll dissect the innovative design and the truly impressive results. Next, we'll look at real-world applications, and lastly, we'll contemplate what the future might hold. So buckle up, it's going to be an exciting ride. So, let's talk about the paper itself. The title is Archerfish, a retrofitted 3D printer for high-throughput combinatorial experimentation via continuous printing. Quite a mouthful, isn't it? A team of researchers from MIT are behind this incredible work, and they set out to solve a significant problem in materials science. High-throughput combinatorial printing, or HTCP, is a really powerful technique, allowing researchers to rapidly test many material combinations and identify promising candidates. The problem is that existing HTCP systems are often incredibly expensive, putting them out of reach for many labs. This research really changes the game. Their clever approach centers on using something readily available and relatively inexpensive, a standard 3D printer. The core idea behind Archerfish is brilliantly simple. Retrofit this readily available 3D printer with the capability for in situ fluid mixing and continuous printing of material gradients. What this means is that instead of mixing materials separately and then printing them step by step, Archerfish mixes the fluids as it prints, allowing for an incredibly fast production rate. And the results? Absolutely astounding. The system achieved an unprecedented throughput of 250 unique material compositions per minute. That's 100 times faster than the current state-of-the-art systems. That's an incredible leap forward, a real game changer for materials research. Now, let's delve into the nuts and bolts of how they achieved this remarkable speed and efficiency. It's time for our technical deep dive. Let's get into the fascinating methodology behind Archerfish. At its heart, it's a modified 3D printer, but with some very clever additions. Imagine a standard 3D printer, but instead of a single print nozzle, it has a custom-designed print head. This head includes a multi-syringe pump and a sophisticated mixing junction. Two different precursor solutions, the raw materials, are fed continuously into this mixing junction from the syringe pumps. These two solutions are then mixed in situ, meaning they are mixed at the precise moment before being deposited as tiny droplets onto a substrate. Now, here's where things get really interesting. This in situ mixing isn't just a simple swirl. It's a highly controlled process. The researchers use a solenoid valve to create pulsations in the fluid flow. These pulsations disrupt the otherwise smooth, laminar flow, creating turbulence and promoting thorough mixing. But that's not the only trick up their sleeve. They also cleverly leverage what's called vortex-induced mixing at the nozzle exit. As the mixed fluid is ejected, the nozzle's design creates tiny vortices, or swirling motions, within the droplets, further enhancing the mixing process and ensuring a homogeneous composition. The whole operation is managed by a microcontroller. This tiny computer acts as the brain of Archerfish, controlling the pump speeds, precisely controlling the ratios of precursors in the mixture, and orchestrating the 3D printer's movements based on instructions written in G-code. The innovation here isn't just about the individual components. It's the brilliant combination of readily available, affordable 3D printing technology with this remarkably sophisticated in situ mixing technique. Of course, this clever system wasn't without its challenges. The researchers faced difficulties in precisely controlling the composition of the material gradients and in maintaining consistent droplet formation. This is something they discuss in detail in the paper. But they found ways to mitigate these challenges, techniques they detail in their paper. Their work showcases that even with these complexities, they were able to achieve that extraordinary speed. Now, let's move on and see what all this amazing technology means for the real world. So, we've explored the ingenious design of Archerfish. Now, let's talk about its real-world impact. The practical applications are incredibly exciting. In essence, Archerfish offers a significant boost to materials science, making the process of rapid prototyping and screening of new materials vastly more efficient. This has profound implications for numerous industries. Think about renewable energy. The quest for better, cheaper solar cells and more efficient batteries is a major focus. Archerfish could dramatically accelerate research in these areas, allowing scientists to test thousands of material combinations in a fraction of the time it would normally take. And it's not limited to energy. The electronics industry is constantly pushing the boundaries of materials performance, seeking materials with enhanced conductivity or flexibility. Archerfish could become an invaluable tool for developing advanced semiconductors, flexible displays, and many other cutting-edge technologies. Beyond these specific examples, this research has a much broader impact on the field. It significantly lowers the barrier to entry for high-throughput materials research. Previously, such high-throughput experimentation required extremely expensive, specialized equipment. Now, many more research groups can access and utilize this kind of technology. This democratization of access means a significant acceleration in the pace of materials innovation. More researchers, with diverse perspectives and approaches, can participate in this vital area of scientific endeavor. Let's paint a picture. Imagine a lab where researchers can rapidly test thousands of potential compositions for next-generation solar cells or high-performance batteries, all within a matter of hours, instead of weeks or months. Archerfish helps make this a reality. It's not just about incremental improvements. It's a quantum leap in capability and accessibility. Before we conclude, let's look ahead to the future of this exciting technology. Let's recap the key takeaways from this fascinating research. Archerfish elegantly solves a critical need in materials science, the need for accessible, high-throughput experimentation. It achieves this by cleverly repurposing a readily available and affordable 3D printer, transforming it into a powerful tool for continuous, in situ material gradient printing. The sheer speed is remarkable, 250 unique compositions per minute. This incredible throughput is made possible by the precise control of fluid flow and the innovative use of pulsation-induced mixing to ensure homogeneity. The researchers conclusively demonstrated Archerfish's ability to rapidly screen materials across diverse systems, positioning it as a powerful tool to accelerate materials discovery. This research isn't just about a faster printing method, it's about democratizing access to high-throughput experimentation, opening doors for a broader range of researchers to contribute to materials innovation. Looking ahead, the authors outline exciting possibilities for future development. Improving compositional control and droplet uniformity are key areas of focus. Integrating the system into a more tightly controlled environmental chamber would further enhance its capabilities, paving the way for even more precise and reproducible results. In closing, this research on Archerfish represents a significant leap forward in materials science. It's a testament to ingenuity and the power of combining readily available technologies with clever engineering. Thank you for joining us on the Future Lab. As a final note, the script for this episode was AI-assisted, which underscores the transformative power of AI in various fields, even podcast production. We welcome your feedback and encourage you to share your thoughts. Join us next time as we explore another fascinating development in autonomous science and AI-driven discovery. Until then, stay curious.